equal to cloud, then screen share. Okay, so as usual, let me just briefly go through what we've done so far within last two sessions. And today my aim is to complete this equation, which is Gauss law. Okay, so this could be delta dot E equal to rho over epsilon naught. So I will reach to this point, and you know that this is in the SI unit and the Gaussian units. One can just represent it via this. So I will complete today this equation and also introduce something called delta cross E, which is the curl of E. And since we are not yet completed to be like a magnetic field, so obviously this term is not there. So we will see how things goes there. So my idea is here to discuss today divergence and curl. Okay. And then in the next session, I will go, because this is a very long topic, this electric potential and work and energy, and they are convoluted. So I will try to cover this in the next session. So what we did so far, we talked about the superposition principle. So I'm going it very quickly because I have already explained this a lot, and we learned about Coulomb's law. Then we solved a lot of problems there. So I'm going it very quickly. Then we started very basic questions that if we have a two charges separated by a distance d, then how one could actually calculate the electric field at some point p. And there was like different versions that if we change the charge instead of q and q, if I change minus q, then it takes like a dipole, and then we calculated the electric field, etc. Then we talked about that how this continuous charge distribution, because always we don't have a discrete charge distribution. So this continuous charge distribution could be a line charge, surface charge, or volume charge. Okay, and then we solved some of the problems from electrostatics, and the conventions and everything was very clear here. That summation, which was for the discrete charge distribution, the summation should go to the integral, so that we can take care of the continuity of the charge distribution. And if it is along the line, then we generally took this quantity as lambda. For surface, it is sigma, and for volumic, that means the three-dimensional object, we take this as a rho. So your basically the charge distribution dq is defined as something like lambda times dl prime, or should be equal to sigma times dA prime, or equal to rho times d tau prime. So this we learned a lot in a detail. And then according to that, we define electric field for the line charge, surface charge, and volume charge. And we're going to get back to this formula again today, and I will give it as a homework to you, that how basically one can calculate divergences and curls by using this definition of electric field. So, and then after, we discussed a lot of problems. So let me just go through it quickly because we had discussed. And lastly, we discussed in a previous lecture that how for a shell and a solid sphere, electric field is varying accordingly. So today's topic, let me now make it in a presentation mode. So today's topic is to understand divergences and curl of electrostatic field, where we going to talk about Gauss law. And first of all, we try to have some intuitive development of Gauss law, and then after I will come later to have a proper way of taking divergences and curl, so that we can define things accordingly. Okay. So we know that electric field is given as, for a single charge, is given as 1 over 4 pi epsilon naught q over r square and r cap. So this is very well known now. So how we can represent this? So we know that from, if it is a positive charge, then generally we say that electric field should go outward. And as in vector, we know that if we denoted something by arrow, so let me take a laser pointer so that I can show you that. So in vector, we know that vector representation is given by something like this. So you put arrow here, and if the length is getting smaller and smaller, it means this vector is having the less value comparing to this, and this vector has less value comparing to this. So this is giving you the magnitude, and this is defined according to the electric field which we are talking about, because it is inversely proportional to the square of the distance. So you see, the moment you go away from this charged particle, the electric field is getting lower and lower. Okay, and that is shown by this vector quantity. So let's simplify this notation, and let's try to define it. So this I already mentioned. So to have the complete idea, I wrote it here that because the field falls off like 1 over r squared, the vectors get shorter as you go farther away from the origin, and they always point radially outward. So this is the complete definition of electric field and its representation. However, there is a simpler way of assigning this as a field line. So we call it as a field lines, and we make it a simpler notations, and we say that, okay, let's define electric field as this. Okay, then you might say, then what about the strength? Because we define here that the moment we go away from this point, the field is getting weaker and weaker. Okay, and that is defined because of 1 over r squared dependence. So this could be a wrong, but no. What it says that what is the density among the, if you wanted to have the calculation of density along the charge or the charged particle, then you see near to this origin, the density is higher comparing to the outward direction. Okay, so this is shown very easily by this representation, which we called formally as a field lines. Okay, so what density means? So the thing which I said, it says that the magnitude of the field is indicated by the density of the field lines, which we are talking here in terms of vector. Now we simplify in terms of the field lines, and we say that this is the density of the field lines. Okay, so it is stronger near to the center where the field lines are close together. So you can see that if you can draw a something like a circle here, then you will see that the density is larger comparing to if you draw a circle here. Okay, so this shows that we are not missing any information which we are explained by representation like this. Okay, so this is the simplified version which we call the field lines to define electric fields. Okay, so if you have any question, please don't hesitate and just ask me there. However,
sir,
yeah,
sir, you said something about circle, sir.
yeah,
what is it, sir?
Yeah, so because we're going to have, I just put one example here, that if we can take a circle, okay, something like this, then we can say that here the density of these lines are higher comparing to at this point. Okay, but sometimes this is just like a symmetrical option which I took here. So this circle, within this circle, you can see the density of these lines are higher comparing to this circle. Okay, what that means? That means that electric field is higher here comparing to the region where we are talking about this. So this representation is same as what we did here. Okay, is it clear now?
Yes, sir.
Yeah, okay, so that's what I wanted to mention. And this is represented by or indicated by the density of the field. Okay, however, you must have one question here, because why I introduced circle. Okay, but before I go there, you will see the concept which we wanted to develop here is something called flux. Okay, so your area could be something like this as well, you know. So if your area is something like this, then the electric field through this area is going to be different than the area here. Okay, so we're going to develop some kind of theory here, and we call it a flux depending on what area we are talking about. Okay, so but before we go here, the question might be like, because if I take this two-dimensional picture, then basically this density is going n over 2 pi r. Is it clear? Because this is a perimeter, and you cut it by something like n number of lines, then density in 2D representation is going something like n over 2 pi r. Then you say that then this is wrong. I mean, because your electric field is basically, is inversely proportional to r square, then it is just represented by 1 over r. So, but in actual picture, what is happening? In actual picture, it is a 3D, right? It is not 2D. So in 3D, you know that if you have a sphere, then the surface area is going to give as a 4 pi r square. Okay, so then you see that the field lines are basically varying as 1 over r square. Okay, so that's why this definition or this representation of field lines are, you can say in a word that it is really justifiable, and one can use this representation. Okay, it's clear, Anamika?
Yes, sir.
Okay, good. So by using that, for just completeness, for opposite charge, if you have opposite charge, then from positive to negative, this field lines are going to be, the direction will be going from positive to negative like this, and it should have a complete circle. It should have a complete. It doesn't mean that it should go something like an infinite. No, it should have something. But yeah, the moment you go away from the charges, this is going to be diminished, like we had just mentioned here, because another mathematical expression also says that because of inversely proportional to r square, this is going to be shorter and shorter, or you can say weaker and weaker when you move from there. And on the other hand, if you have an equal charge, this is going to repelling kind of thing. Okay, so this is just a kind of concept which one should know about electric field and representation by field lines. Okay, so this development basically, or you can say this model, this model is basically giving you a concept which I defined here, something called flux. That means that electric field through a given region have what strength. Okay, so let's define it mathematically. So flux is basically defined as something with a notation here, phi e through a surface S. Okay, and it is something called integral of E dot dA. So dA is the infinitesimal area of the surface you are defining with the dot product of electric field. So this is defined as called flux. Okay, so what it means? It means it's a measure of number of field lines passing through S. Okay, and that's what I showed before, that you have some area and how many number of field lines are basically passing through that particular area. So this quantity is a very important quantity called flux of electric field. Okay, and yeah.
Sir, flux field lines, number of field lines passing through S, it should be perpendicularly, no, sir?
Yes, that's what we are going to have this now. Okay,
Okay.
so because you can also have some angle, but then the maximum strength is only when it is perpendicular to that surface, right? Because it is a dot product, and dot product is what? Dot product is basically the cosine theta. And if it is perpendicular to each other. So let me just explain it. Let me just explain it by what I mean this. So you can see here that E dot dA is proportional to the number of lines passing through the infinitesimal area dA. So this could be seen as this picture. So dA is basically normal direction through the surface we are talking about, and we're going to calculate this electric field, which is making the, you see some angle with dA. Okay, so this is defined as flux, and these are some qualitative way of representation that this suggests that the flux through any closed surface is a measure of total charge inside. So you can see that, for example. So this is a very arbitrary, surface we draw from two charge configuration. So this is of a strength twice of this charge. Okay. Then these are, you can just make some flux line, whatever you want. This is just a representation. So now you see that electric field is coming out from here, and then the configuration basically state that how within this closed surface, how much electric field lines are basically passing through that charge. Okay, so this is just a qualitative way of representation. However, you can see that if the charge is outside, okay, then outside the surface, then you can say that the total flux having no contribution at all, because if the charge is within this surface, then from wherever electric field is going out, you can calculate that. Okay, but what about this? So you, for example, charge is here, and you draw a surface like here, then electric field. So incoming electric field is basically outgoing electric field. So basically, they are going to cancel each other, and then you can see that the strength is basically 0, or you can say nothing. Okay, so these are some qualitative definition of flux, and next we're going to see how to use this in a various numerical problem, and how we can develop a very general theory or general law, which we call a Gauss law. Okay.
Excuse me, sir.
Yeah.
Sir, can you explain the second one, sir, where you said that it will cancel each other?
Yeah, so you see here, it's the incoming, the electric field is incoming here from this in this surface, right? And it is going out with the same strength here, because it is just, you can see this is just like a hole, right? So once a charge is outside the surface, it is not going to contribute to the total flux, because it is just like its income from, it's in from one point and just going out from other. So basically, it is going to be like, you can say, if you define inside as a negative one and outside as a positive one, it is going to cancel out. What are you going to count there? You understand my point? So flux is basically not going to count if you have a, and you will see some numerical problem. Okay, then maybe it's going to be more understandable. Okay.
Sir.
Yeah.
This is for both kind of charges, if it's positive and negative also.
Yeah, no, I mean, if you have a, see, this charge is basically outside the surface.
Yes, sir.
Understand my point? And if you have a charge inside the surface, the area which you have taken, then flux is going to count, because you can count that, okay, I mean, because of this charge configuration from this, one electric field is going, 2 going, 3 going, like this, but here one is incoming, one is going out, right? So,
yes, sir.
So basically contributing nothing to the total flux, total flux is going to be 0, right? So this is going to be more clear. Okay, I mean, I will give you some numerical problems on that. Okay, very good. So Gauss law basically states this. So in case of a point charge Q at the origin, the flux E through a spherical surface of radius r is going to give you. So you see here integral, we took the integral, but a round circle over there. That means it should have a closed surface. Okay, so if you wanted to calculate a flux, it should have a closed surface. So not like an open surface, which I just gave one example there. Okay, so this surface should be, I mean, this integral should be the dot product of electric field and the infinitesimal area which you wanted to calculate. So what that means, if I just put the values in a spherical polar coordinate and suppose that it is a spherical surface, so electric field is, that this is given as 1 over 4 pi epsilon naught q over r square r cap. This we know. And this dA for spherical polar coordinate system, which you learned in your mathematical, and I revised these things before I started the sessions. So this is going to give you r square sin theta d theta d phi r cap. Okay. Now what you need to do, you need to just integrate by canceling the term which is constant or whatever. So what is going to happen? This r square is going to cancel out, and then the integral will be over theta and d theta, sin theta d theta and d phi. And d phi we know that this is going to give you integral of 2 pi. So when you calculate this, which we did last time actually, when we calculated the spherical, object was there, and then we calculated the electric field. So we did this calculation. So once we have this, it is going to give you q over epsilon naught, because this 2 pi factor is going to cancel by this 4 pi. So only 2 remains. And then when you integrate sin theta d theta over the range of theta, then that is also going to cancel out one of the 2 factor. And then r square is already cancelled out, and r dot r is going to give you 1. Okay, so this is going to give you q over epsilon naught. Okay, so this is this is just a simple example for a spherical surface of radius r, and how to calculate the flux of electric field through that surface. Okay, so what that means, that evidently the flux through any surface enclosing the charge is given by q over epsilon naught. Okay, so this is the definition of flux which we developed, and this we call Gauss law. Okay, so always we don't have such a situation that you have the spherical surface. For example, in case of line charges which we see, I mean, you can't make it a spherical, right? You have to have a kind of cylindrical symmetry. Or sometime also you can have something like a plane, like we see that this is a 2-dimensional plane, and we wanted to calculate electric field out from that surface. So one could have a plane symmetry. So in general, when we take the application of Gauss law, okay, so sorry, but before that, I just wanted to mention that this electric field is nothing but sum of all the electric field, as we know from the principle of superposition. Okay, because sometimes it happens that instead of a single charge at the origin, there are a bunch of charges scattered about. Okay, so we can use this electric field as the vector sum of the individual fields according to superposition law. So now come back to the symmetry which we are talking about. Okay, so let me complete first, and then I will talk about symmetry as an application of Gauss law again. Yeah. So if you have electric field, like sum of all the charges, and then you have the vector sum of this, then this flux is basically have the generalized definition where you have a closed integral of E dot dA equal to sum over I equal to 1 to n, because this electric field is from the n charge distribution, and then you just have the integral of all the individual electric fields time with the dot product of the area, the infinitesimal area we are talking about, and this will basically giving you sum over I equal to 1 to n qi by epsilon naught. So where Qi is one charge, like Q1 plus Q2 plus Q3, etc., like Qn. So for closed surface, we can say that flux is basically in general defined as Q enclosed divided by epsilon naught. So this is same definition which we did for the single charge. Once you have a multiple charges, discrete charges, then we can just sum off all the charges like Q1 plus Q2 plus Q3, etc., divided by epsilon naught, which we represent as Q enclosed or QENC. Okay, so this is the overall definition of Gauss law. And then I hope there is no question, Namika. Is there any question on this?
No, sir.
Yeah, good. So this is a very general definition we can make for the Gauss law. And then what we see here, that this is the integral form of the Gauss law. Can we write it as a differential form? Okay, because that is also very useful. Sometimes your electric field is given and differentiation is easier than the integration. Okay, so we can represent this Gauss law from integral to differential form. Okay, and how we can do that? So I think in last session in mathematical physics, you learned something called the divergence theorem. Okay, so if you are integrating something over surface, you can convert it into volume by having this, divergence of this vector times the volumic area. Okay, so it is just like a d tau, it is volume. So dx times dy times dz in a Cartesian coordinate, but in a spherical polar coordinate, it is going to change accordingly, etc. Okay, and this is very important, that this is going to have something called divergence or delta dot E. Okay, so we know from the divergence theorem that integral of this quantity can be written as divergence of electric field, something like this. And Q enclosed by epsilon naught, we know that the definition which I shown before, that this is nothing but the charge, you can write in terms of the charge density. So if you have a volumic representation, then you can use this rho. Just I focus that for a linear distribution, it could be something like lambda times dx or dl. Okay, if it is surface, then it is sigma times dA. However, in general, we can, in the volume sense, we can say that Q enclosed should be integral of volume over rho d tau, where rho is the charge density, right? So we have now left hand thing written by the divergence theorem, and right hand we can write in terms of volume integral in terms of the charge density, like this. So if I now make it equal, because these are equal things, then we can write that integral over volume delta dot E d tau is equal to integral over V rho over epsilon naught d tau. So this step is clear, or any confusion?
No, sir, no confusion.
Yeah, good. So by having this, now you can remove this integral sign, because now you have a volume integral both sides, and then d tau is going to cancel out. You can say that delta dot E equal to 1 over epsilon naught times rho. So this is called the integral form of Gauss law, and this is called the differential form of the Gauss law. Okay, so that's what the thing which I showed in a very first slide, that today's my target is to reach up to this equation. Okay, so this is very, very important in terms of this is this is just a derivation which we did. So we started with something called field lines, and field lines basically give you an idea of flux through any surface area. Okay, and then the idea of this flux basically gives you a integral form of Gauss law, which we can change into differential form by using a divergence theorem, and this will give you a very kind of idea, or you can say this is just like a mathematical manipulation one can do, so that a law can be changed from integral to the differential form. Okay, so you understand now the point that why one should need to define a field lines, because field lines give you an idea of flux, and that flux is basically giving you an idea about the Gauss law. Okay, so after developing this, let me talk about what I basically started talking about, the symmetry. That application of Gauss law requires a very symmetrical kind of configuration, and which we know, or I know, the symmetry which we can apply for this law is spherical, cylindrical, or plane symmetry. So what that means? So it means that if you have, for example, some distribution of of a sphere, which we talked about in a previous session, with a radius r, then one can make a Gaussian surface something like this if you wanted to calculate field outside this sphere. Sometimes we can also interested to calculate electric field inside this. So this r could be reduced, and then you can draw a Gaussian surface inside that and try to see that what are the total charge enclosed, and you just divide by epsilon naught, and obviously one terms you can calculate in the integral form like this or in the differential form like this. Okay, similarly for a cylindrical, like a kind of line charge, if it is distributed along the line, then you can draw something like a Gaussian surface, something like a cylindrical. Okay, so this is the symmetry requirement for the Gauss law. And for the surface which we are talking about, we can have a Gaussian pillbox, something like this. So you can see that this is just a rectangular surface we have, and then we draw something like a box which basically goes down from this surface and also up from this surface. So this pillbox is basically the plane symmetry which we require for the application for the Gauss law. Okay, so by having these things in our mind, let's so we developed a very beautiful law which we called Gauss law. Now one could also talk about some application of this. So let's start with some numerical problems so that we can get into it. Okay, so I hope there is no question till now, Namika, so that we can yeah. So let's suppose now, however, these problems are very easy to handle, but I'll give you some idea that how this problem can be solved. So suppose the electric field in some reason is found to be electric field is equal to k times r cube r cap. Okay, in spherical coordinates where k is some constant. Then the question is asking that find the charge density rho and find the total charge obtained in a sphere of radius r centered at the origin. So did you understand this question, Ananta?
Sir, second question, I didn't understand.
Okay. So first question is clear, right? That electric field is given in terms of some distribution in spherical coordinates. Okay, it is k r cube r cap. Obviously, there could be some theta and phi, but those terms are zero here. All right. So electric field is given. Now one has to calculate charge density. So how are you going to calculate that? Any idea? Can we use Gauss law here, the things which we developed, or the definition of flux which we developed?
Yes, sir, we can.
So what formula is going to apply for this charge density rho?
Differential form of Gauss law.
Very good. So what we need to do, it's very simple now. Now you understand that rho can be written as epsilon naught times delta dot E, right? This is the differential form of Gauss law. And what you need to do, that in a spherical coordinate system, this delta is basically, because it is just r dependent, Obviously, there is a, as I said before, that there is no theta dependence or phi dependence. So one can just take this form. And then this delta dot is basically, or delta is written as 1 over r squared del over del r in spherical coordinates. And then electric field is basically, given as kr cube. You know that this term basically, this term basically comes from the spherical polar coordinates, okay, as a definition of delta. And this I actually introduced in a very first session accordingly. So if you don't remember, please revise it, then you're going to get it very easily. So up to this is delta dot. So, and then you have to put just like electric field, which is kr cube. And, you can do it very easily now. So this is r to the power 5. K is constant, so K is going to be outside. And when you differentiate it with respect to R, then it's going to give you a 5 times r to the power 4. Okay. And then this r square is cancelled with this r square here. And this is going to give you now 5 epsilon naught kr square. So these steps are clear, no?
Yes.
Good. Now you said that second question. So find the total charge contained in a sphere of radius r centered at the origin, which I think is very easy now, So the spherical symmetry which we talked about, we're going to use that. Okay. So according to Gauss law, Q enclosed is what? Epsilon naught integral of E dot dA, right? And then what you can do, so you can simply put the values now, and you know that if it is a spherical, because let me go back to this. So this is something like this situation. Okay. So by this situation, we can say that this dA is nothing but 4 pi r squared because it is a spherical surface. Okay. And electric field is given as kr cube because the integral is going to be from 0 to r. Okay. So let me write it so that you can. So this is going to from 0 to r. And therefore, you're going to get 4 pi r square as the surface area for the spherical symmetry thing. And then this is, since this is integrated from 0 to r, so this r cube is basically, it is going to be simply kr cube times 4 pi r square, and then r cube and r square is going to give you r5, and then 4 pi epsilon naught is there. Okay. So this is the one way of doing things. Okay. What another way is that? Another way of doing this is by using this definition. Okay. By direct integration, you can use this formula, which we developed in problem number A. And you just write Q enclosed as rho d tau, and then integrate over 0 to r, and substitute this value of rho, which you find already. And this d tau is nothing but 4 pi r squared dr. And once you do the integration, you're going to get the same answer which we got here. Okay. So you see, this kind of problem can be asked in like a MCQ type of questions in your competitive examinations. Okay. So just get into that, and you're going to see things very clearly. Okay, so let's suppose now another problem. So let's read it. It says a charge Q sits at the back corner of a cube as shown in the figure. So what is the flux E through the shaded area? How we can approach this problem? Namika, if you have, can we use Gauss law here?
Yes, sir.
And how? How are we going to draw the surface? I mean, the Gaussian surface.
Sir, it's a plane, so I think last one means 3 were there, no, sir? Gaussian plane.
Gaussian pill. Are you
Yes.
sure? With the Gaussian pill, can you calculate this? Because you see the charge is sitting here in one of the corner of the cube, okay? And we wanted to find area here. Charge is not distributed over plane. You understand my point?
Yes, sir.
So we
that
can't
means
use that. No?
second one, sir, line.
Again, you see, you are mistaking again. Your charge is a discrete, a single charge. It's not distributed over line, not distributed over a plane. It's not distributed over a sphere.
Yes, sir.
You understand? This is a discrete charge. This is a single discrete charge sitting at the corner of a cube.
Yes, sir.
And because of this cube, what is going to happen? Obviously, electric field is going to be like this, and it is passing through all the surfaces,
Yes.
right?
Yes,
But
sir.
we wanted to find only the flux through this surface.
Okay,
So
sir.
you understand the question? You see, this is very important, you know, that you must understand what question is basically asking here. Okay. So let me do this question. This is very interesting question actually. So what you can do, you can understand that this Q can be a part of you know, a surface. Let's suppose, let me just, you know, give the figure. Think that this cube has one of the 8 surrounding the charge. Can you do that? You understand this? So let's suppose this was the cube. Okay. Now you have one of the cube which can be something like this. Then in the back of this cube, there is one more cube. Similarly, in the back of this cube, you have one cube here. So you have a 1, 2, 3, 4 cubes. And then the symmetry requirement is what? That you can also have 4 cubes below these 4 cubes. Okay. So this is another cube. And in the back again, there is one cube. One cube is here, which you can see. And then in the back again, you can have one cube. So what that means, this charge is now surrounded by 8 such cubes. Now you can see that this is a very symmetric, right? Okay. So how many surfaces now we have? Such kind of surface. Can you count it for me? If you have such a symmetry, then how many surfaces you're going to get? So you can see that, for example, in here you have a 4, right? Similarly, you're going to get 4 from here. And also below 4, and then this side also 4. So in total, if you calculate, and also the surfaces which are here, they also have a 4, 4, 4. Okay. So in total, you're going to get
16.
Are you sure? Or
Okay,
is
sir.
it 24? Right? Good. So now you have a 24 squares which make up the surface of this larger cube. Okay. And gets the same flux, you know,
So what
and all
is
the
that?
surfaces. Yeah. So that's the symmetry, you see. And now all the surfaces getting the same. So what do you mean? What we're going to do? So for one surface, we're going to just divide by 24, right?
Yes, sir.
And then it is going to be like one phase of E dot dA is nothing but 1/24 of the whole large cube E dot dA. And you know that from Gauss law, it should be Q enclosed divided by epsilon naught. So this term is basically nothing because we have a only single charge here. So this is Q divided by epsilon naught, and 1/24 factor basically comes from the symmetry requirement. So it means from one of the phase here, we're going to get 1/24 Q epsilon naught. You know, these are very frequently asked questions in your, you know, any exams, like any competitive exams, where even you can, you know, do this practices very easily, and you know, you're going to get that. Okay. So let me go a little bit faster because I have to cover divergences and curl also. But yeah, if you have any question, please, you know, let me know. Okay. So let's again apply this Gauss law for a charged solid sphere of radius r with total charge q, which we have already solved by integrations in last session, but that integration is very cumbersome, and you need to first do this with the spherical polar coordinate, and then you integrate over everything. So now we're going to use Gauss law, and then you will see that how problem is basically reducing simple manner. So let's suppose we going to imagine a surface of radius r greater than r, means outside. Okay. So by having this, what you can write, Gauss law says that this should be integral of EdA equal to Q enclosed divided by epsilon naught. Now you can use this formula, and you can say, because the total charge is given as Q. Okay. So Q divided by epsilon naught. A simple formula, because Q enclosed is Q, so Q by epsilon naught. Now we should bother about only E dot dA. Okay. So for this, actually, from wherever electric field you calculate, you will see that this is a normal surface, So it means the electric field you can write in terms of, because this dot product is like normal to each other, you can write that this could be E dot dA should be write as a modulus of E, which is the magnitude of E times the dA. Okay, from that surface, as you said in the in the definition of flux. And also we know that because of this single charge Q, which is surrounded on there, so all the electric field through this Gaussian surface is going to be constant. Okay, so we can take out that from the integral like this, and then you have to integrate dA. So this dA is basically nothing but 4 pi r square, which we know very easily. Okay, so by using Gauss law, you see that how problem reduced for a very simple reason, and this should be like equal to 1 over epsilon naught times Q, and therefore electric field is defined as E over 4 pi epsilon naught Q over r square for this, for this Gaussian surface. Okay. So these are some of the examples that one can take over, and I left few things for you also, that you go back and verify everything what you did with the integration, etc. This is just one of the examples which I wanted to put in there.
Excuse me, sir.
Yeah.
Sir, can you explain the last problem again, sir? Why this E is like magnitude of E? How?
Which one? This one.
Yes, sir.
Yeah, so you see, I mean, first of all, you have to write E dot dA, okay, the dot product of this. So we know that maximum is possible when you have a simple, configuration where you have to take the modulus of, because that dot product of two vectors is what? It is just like the magnitude times, the cosine theta or accordingly, right? Yes. So by using that, you get that this is modulus of V, and then the modulus of dA, and the maximum value is just the product of this. Okay, because minimum value will be like 0, right? Which we don't have here. Now, from this surface, you can see that electric field is always going to be constant, of the same magnitude everywhere.
Yes, sir.
So it is not dependent on any other things. So you can take this take out from the integral, and then you have to integrate only dA, because whatever dA you take, anywhere you take, this electric field is going to be constant, right? So that's why we take out from this, and then you integrate over all the area here, surface area, which is 4 pi r square, and then you're done with the calculation. Okay, so you can see these applications for shell as well. The shell which we calculate, suppose this is a shell rather than solid sphere, and you draw a Gaussian surface inside. So you know that inside the shell, the total charge is going to be 0. So you can simply, from the Gaussian surface, you can say that electric field is going to be 0. Simple. Which we calculated, in the last session, we calculated by integration, etc., blah, 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 But it is very easy now that you apply the Gaussian surface, and you're going to get that very easily. Okay, good.
Yes.
So similarly, one can do for something like charge density in a cylindrical manner. Okay, because I just choose one of the examples so that all the symmetry can be covered here. So it says that a long cylinder carries a charge density that is proportional to the distance from the axis, which is given as rho equal to Ks for some constant K. Okay, now find the electric field inside this cylinder. So here now, since distribution is over the cylinder, then we can use the cylindrical symmetry accordingly. We will make the Gaussian surface to be cylinder. So which could look like this. So you have a cylinder, okay, and you wanted to calculate, and this rho is given as K times S, where K is the constant, and S is the simple, from the center, this distance is called S, or you can say the radius of the cylinder. Okay, so what you can do, you can draw a Gaussian surface, and all things are defined here, and accordingly, the electric field should be given as something called 1/3 epsilon naught Ks square S half. Okay, so probably this is given, and similarly, yeah, this actually I just make the solution here because I wanted to give you it as a homework. Yeah, similarly, maybe if you able to do this by yourself, then what you can do, I would suggest that you can just try to make it in a page, scan it, and send it by email. Okay, so that I can check that you going to get the same answer or not. If you have any problem, obviously you can ask there as well. Otherwise, in the next lecture, obviously I will explain it more clearly. Second problem which I wanted to give you as a homework, like this. So if you have an infinite plane carries a uniform charge surface sigma, find its electric field. So what you can do, obviously you can make a pillbox, and then the answer should look like this, which is equal to sigma over 2 epsilon naught n cap. Okay, you can make it, Namika?
Oh,
Yeah, please try these problems. Okay, maybe just take a screenshot or whatever, and try to make these problems and send me the solutions. Okay, then another problem, this is also kind of homework I wanted to give you, that two infinite parallel planes carry equal but opposite uniform charge densities plus minus sigma, like this. Okay, so these are two planes, but this plane has a plus sigma and this plane has a minus sigma charge density, but this is uniform, so it is just like a overall it is distributed over this plane. Now we need to find the field in each of the three regions, like 1, 2, 3. So this one is to the left of both, then second region is in between, and third one is the right of the both. So can you guess the answer? Maybe just let me give you the hint. Hint is this. So your answer for a plane for the electric field is given as sigma over 2 epsilon naught n cap. Okay, so can we use this formula to solve this problem? Okay, let's suppose that there is no region 2, there is no region 3. Just calculate the electric field at region 1. What it could be? And you know from this, for a surface charge, there is electric field sigma over 2 epsilon naught. Think about the field lines which we developed, which we started with the, the concept was developed from the field lines, and then we talk about the electric field, electric flux, and etc. Okay, let me give you one more hint. What could be the direction of electric field on this surface due to this due to this
Outward.
plus sigma. Yeah, in reason 1, it is outward. Okay.
Yes, sir. Yes, sir.
And because of this minus sigma, what could be the direction in this reason?
So reason 1 only.
Yes.
Um,
Yeah, we are talking about reason 1 only. Okay.
okay, sir.
So it is just like, let me
Inwards.
draw it. So this is my plane. This is my plane. Okay. This is plus. This is minus. Okay. And we wanted to find electric field here. What is going to happen? So because of this positive, you know that this could be
Outwards.
outward. But because of this negative, at this point, what is going to happen? This could
Inwards.
be.
Inward.
So what could be the total electric field then?
0.
0. This is so simple, right? Similarly, what about this third reason?
Right side.
So for third reason, because of this, electric field is here,
Inwards. Yes.
in this direction. But because of this is positive,
Outwards.
so electric field is outward. So again, what is going to happen?
0, sir.
Right. What happens here?
Yes.
In between, what is going to happen?
Uh,
Again, because of the positive charge,
hmm.
it is going to be outward. Okay.
Yes. Yes, sir.
But because of this negative plate, what is going to happen?
Again inwards.
It is
Oh,
side
sorry.
again.
Okay, sir.
You understand?
Yes.
That's
sir.
the beauty of the problem, you know. You are trying to first get from this. So
Yes,
this
sir.
is outward. Now you are trying to get the field because of this negative. So this is inward.
Oh, okay, sir. Yes.
So in between, you have a sum of this electric field. And you know that from the plate, for the plate, in a very first situation, we know that for the plate or the plane, E is given by sigma over 2 epsilon naught. So for one plane, E over 2 sigma epsilon naught, for other plane, again E over 2 epsilon naught. And these are going to be sum up, and it is going to give you, you know, you understand now
Yes, sir.
that this is the picture. So this is sigma over epsilon naught, because half factor is going to sum up to 1. Okay.
Yes.
So this is the whole picture of such situations. Okay. So I hope, I mean, this is interesting, and you know, you get the point which I wanted to make here. So this is very interesting problem. So please try to go through it, and let me just quickly go for the divergence and curl, and you know, I will stop there. So divergence means we wanted to calculate delta dot E, okay, which you can do very easily, because you know that electric field is given by 1 over 4 pi epsilon naught r square, blah blah blah. Okay, so by substituting that and then calculate delta dot is very easy. Okay, so let me just roughly do this. For all space in general, we know that ER is given as 1 over 4 pi epsilon naught integral of all space r cap divided by r square, and then the charge density. Okay, so we can use you know, now delta dot E. So what we need to do, I mean, obviously 1 by 4 pi epsilon naught is constant, so it's going there, and then integral delta dot of this quantity. And if you remember, this I introduced in a very first session, which we call Dirac delta function or delta function. Okay, so by using that, delta dot r cap divided by r square equal to 4 pi chronicle delta cube. Cube means because this is 3 surface. Okay, I mean, we are talking in 3 dimensions here. If it is 1 dimension, then we can generally say chronicle delta r. Okay, but this is or x rather than r, we can say x or delta y or delta z. But this is 3-dimensional object, so we call it delta 3 r. So by using this formula, we can develop something like this, because we know by definition this r is nothing but r minus r prime. If you remember the notations which I used in a very previous sessions. Okay, so just substitute that, and you're going to get the divergence as rho r divided by epsilon naught, which is nothing but a differential form of the Gauss law. Okay, so previously what I did, if I just give you the concept again, we talk about electric field and electric field lines, which develop the concept of flux. And then intuitively, we got something called Gauss law, which basically give you the integral form. And by using a divergence theorem, we say that this could be written as delta dot E equal to Q enclosed divided by epsilon naught. But when you do this mathematically, you have to use some mathematics here, and then you again going to get the same thing, which is written here. Okay, so you can now write in the integral form or whatever, and then rho can be written as again Q enclosed, because this integral of rho d tau is Q enclosed, and therefore you want to get this. So please work on these things by yourself, okay? And if you have any problem, obviously you can ask. Similarly, if I go to the curl of delta E, delta cross E, what you assume? What you wanted to get? Should it have some value or something? Are you there?
Yes, sir, yes, I'm there.
Yeah, okay. Because the electric, think about that what we are talking about electrostatic field, right?
Yes, sir.
And definition of curl, what it says, if you remember, I gave you some explanations that when something is in dynamical way and it is curling out, then you can get some value of curl. But here we are not talking about any such field which is actually moving. So,
Yeah.
so what it should be, curl should be simply equal to a zero vector, but you need to prove it, okay, which is very easy to do. So again, by definition is this, okay, and one way of this is that you can just substitute this value as we did for the calculation of divergence and use mathematics, which you can do very easily. But I am giving you the alternative method where we can suppose that, let's suppose that a charge is basically moving from point A to point B, and we wanted to calculate a quantity, something called E dot dl, okay, rather than E dot dA, which we calculated previously. We wanted to calculate E dot dl, okay. So in spherical coordinates, what you can say that dl is given by dr r cap plus r d theta theta cap plus r sine theta d phi cap, okay. So by using that, you can write E dot dl as 1 over 4 pi epsilon naught q over r squared dr. Why? Because there is no theta component, there is no phi component. So E dot dl is basically just dependent on dr, which is this one. Okay, this is clear now?
Yes,
because
sir.
you see, electric field is just r cap. But in general, so I'm just giving you an idea that in general, if this electric field, maybe when you go to higher mathematics, then you will see that this could be dependent on theta and phi as well. Then obviously this expression is dependent on theta and phi as well. Okay, but for the time being, whatever definition we have, let's do this. So by having this, now what you have to do, you have to integrate over this from A to B, which is very easy now, because when you do the integration, you will see that this is q over r squared dr going from A to B, and 1 over r square is nothing but minus 1 over r, because and this is the integration. So, and then you have to just put the final limits. So this is going to give you 1 over 4 pi epsilon q over ra minus q over rb. But in case, since we are talking about a kind of spherical symmetry or something, so this A and B point is going to at last going to be like an equal point. Okay, so in that situation, you're going to get, when ra is equal to rb, then you're going to get this in line integral basically going to be 0. Okay, and
Yes, sir.
therefore we can apply the Stokes theorem, which you learned actually last time. You can say that delta cross A equal to 0. Okay, so this is just an idea that alternatively we can also prove that the curl of E is nothing but equal to 0 for a static charge distribution. Okay,
Yes.
so these are some of the ways, where as a homework I would say that use this expression which we used for the delta dot T and try to prove that this is basically 0. Okay, so just use this expression.
So that is
And
I'll have to prove so.
yeah, so I mean you have to prove that delta cross A equal to 0, but
Yes,
you
sir.
use the electric field expression of this, right, which we used for delta dot T. We use this now.
Yes, sir.
Okay, and then we use this delta dot T. So rather than delta dot T, you have to just put this like a delta cross E and then try to see that what you are getting. And obviously, you know that this should be equal to 0. Okay, answer is very clear to you. So this I gave you the alternative way of using this and applying the Stokes theorem. This line integral can be changed into this integral, and then you want to get delta cross equal to 0. Okay.
Yes, sir.
So in the next lecture sessions, we're going to define electric potential, and this line, and that's why we introduced this idea of line integral here, because this line integral is going to be very helpful when we talk about the electric potential. Okay, so this could be written in terms of line integral of A dot dl, and which can be converted into something called E equal to minus delta V. So we're going to see this in the next sessions. And till now, I gave you a lot of homeworks to do. So hopefully you remember that what homeworks I had given.
Yes.
And, with this. And if you wish, as I said, you can always send it by email by scanning your documents. And I will try to explain it more if it is needed, then I will obviously explain it in the next sessions. Okay, good.
Yes.
So no question?
No,
Shall
sir.
I stop now?
Yes.
Okay, good. So thanks a lot for joining, and
Thank you, sir.
stop recording.